So in this video, we're going to do some Taylor polynomials and approximations, and we're going to see what they are used for. So first, to start off, a little review. So given this function, x squared minus 2x plus 2, I want you to write the equation of the tangent line at x equals 2. So here's a graph of the function. It is a parabola. We're going to get the equation of the tangent line to the point when x equals 2. So this should be pretty basic. This should be a review of your basic calculus abilities. So to do this, we're going to first want the point of tangency. So at what point is the line tangent to the curve? So to do that, we're basically going to calculate f of 2. Since x equals 2 is our x value of concern. So f of 2 is going to be 2 squared minus 2 times 2 plus 2, which comes out to 2. So the point of tangency is 2 comma 2. The next thing we'll need is the slope of that tangent line. To calculate the slope, we're going to need the derivative. So f prime of x is 2x minus 2. So if we input 2 into that, f prime of 2 is going to be 2. So the slope of our tangent line is 2. So with these two pieces of information, we can write the equation. Let's write it in the form y equals mx plus b. So I'm going to input my point of tangency and my slope, so that I can be able to solve for the y-intercept. So based on this calculation, the y-intercept is negative 2. So I'm able to write my equation of the line, y equals 2x minus 2. So looking back at my graph, the equation of this line is y equals 2x minus 2. So why I had you do that, that is basically the idea behind a Taylor polynomial. You're trying to create a polynomial that is an approximation to the curve around the point of tangency. To expand upon this idea, here is a rough sketch of a graph of a cubic. I'm going to draw a line of tangency to this cubic. So this is a linear line of tangency, a degree 1 approximation to the curve around that point of tangency. Well, what if I wanted to go a degree higher? How would it look if I had a parabola that was used to approximate values around that tangent point? Well, that would be a degree 2 approximation. So a higher degree approximation. That is the idea behind these Taylor polynomials. They are higher degree approximations centered around that tangent point. And you can kind of see by the graph I've shown here that as you get a higher degree approximation, the approximation gets better, right? With each higher degree, you're kind of getting closer and closer to the original curve. So the higher your degree, the better the approximation is going to be. So there is a formula for these Taylor polynomial expansions, and I'm going to give it to you here. So the Taylor polynomial expansion to degree n, centered around the point x equals a, is going to look like this. So for now, just kind of write it in your notes. We'll get some practice using it, and when you get some practice using it, it'll make a little bit more sense. I know right now it looks a little daunting. But basically here is the expansion. This is what's going to get you all of your terms in the polynomial pretty quickly. Again, this is centered around the point x equals a. So let's go back to our original problem when I wanted to find the line of tangency, and let's use this Taylor polynomial formula. So if you recall, the original problem, number 1, had this parabola f of x. It was x squared minus 2x plus 2, and we were centered around the point x equals 2. That was where the tangent point occurred. It was centered around x equals 2. So let's find the Taylor expansion to degree 1, and again we're centered around x equals 2. So how's that going to look? Well, using the formula that I just gave you, that polynomial begins with f of 2. Then we're going to add f prime of 2 times x minus 2. So let's just calculate these out. F of 2 is 2. I need to find f prime of 2, so that's going to help if I have f prime written out. Again, we know f prime to be 2x minus 2. So what is f prime of 2? That is 2 times x minus 2. So a quick computation of that gives us 2x minus 2. And that definitely was the equation of the line of tangency. So this agrees with our first answer. So hopefully you can begin to see what these Taylor polynomials are going to be used for. We're going to try to make approximations centered around that point of tangency. The higher the degree, the better the approximation is going to be. So that being said, let's go back and let's redo that same problem we just did. So we're going to continue to use that f of x equals x squared minus 2x plus 2. But let's do it to degree 2. So we're going to get one more term in our Taylor polynomial, and it's going to end up being to degree 2. It's still centered around that same point of tangency when x equals 2. So using that Taylor formula that I gave you earlier, we need to start with f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared. And here, pick up a factorial. So it's all going to be over 2 factorial. Okay, so we have a little bit of computations to do here. Starting with f of 2. You already knew what that was. That was 2. I'm going to need some derivatives here. So my first derivative, again, is 2x minus 2. And I'll get myself set up with f double prime. That's just 2. So, plugging in the rest of the way, I got 2 times x minus 2 plus f double prime of 2, which is 2, all over 2, times x minus 2 squared. So it's a bit of a computation here, but you should be able to do this. When all is said and done, and you combine like terms, simplifies to x squared minus 2x plus 2. And that should be no surprise that it is the exact same equation as the original problem. So our second degree polynomial actually is the graph itself, which should kind of make sense. When I go from the linear tangent line to a higher degree polynomial, it basically is going to wrap directly around the original polynomial. So the approximation isn't an approximation, it's an exact calculation to what the original curve is. So taking that idea a step further, that each higher degree term, each next term in the Taylor polynomial requires another derivative. For that reason, these Taylor polynomials will oftentimes be used for functions in which there are an infinite number of derivatives. That basically the derivatives can keep you can keep getting a derivative, that there is no end to the number of derivatives you can take. So what functions provide that? Functions like e to the x, functions like natural log x, or sine x. You can keep taking derivatives and repeat that process for an infinite number of derivatives for these functions. So the last thing you got to know for these Taylor polynomials is if you're doing a Taylor polynomial and you are centering around x equals 0, if you're centering around x equals 0, there is a special name for that Taylor polynomial. That Taylor polynomial is called a Maclaurin polynomial. So if you ever come across that name, Maclaurin, in your problem, it is basically telling you that it wants you to center around x equals 0. So let's put all this together and let's do an example. Find the third degree Maclaurin polynomial for f of x equals e to the x and use it to approximate the value of e to the power of 0.1. E to the x has an infinite number of derivatives, so we could find an infinite degree polynomial, and with each higher degree we'll get a better approximation. But in this case I want third degree. We're doing a Maclaurin polynomial, so again we're centered around x equals 0. If we're going to find third degree, I'm going to need 3 derivatives. Well, e to the x is pretty simple. my first, second, and third derivative are all e to the x. So that should make life a little bit easier for us. So with those derivatives in place, let's write out that Maclaurin polynomial. First, I need f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 all over 2 factorial times x squared. I didn't write x minus 0 this time, plus f double prime of 0 all over 3 factorial times x cubed. And again, I just didn't write x minus 0. So there is my third degree Maclaurin polynomial. Let's do some calculations here. F of 0 is e to the 0, which is 1. F prime of 0 is also going to be 1. So 1 times x. F double prime of 0 is 1 over 2 factorial. That's going to be 1/2. And then finally, f 3 prime of 0 is also going to be 1. So 1 over 3 factorial is 1/6 times x cubed. So there is my third degree Maclaurin polynomial. So let's use that to estimate e to the power of 0.1. So I'm going to plug in 0.1 into this Maclaurin polynomial, and let's see what we get. 1 plus 0.1 plus 1/2 times 0.1 squared plus 1/6 times 0.1 cubed. So when I plug that into a calculator, you get a long decimal here. 1.10516667. And if you get the exact value of e to the power of 0.1 on a calculator, the exact value, 1.105170928. So it looks like we're actually correct to 4 decimal places. So my third degree Taylor polynomial is a very close approximation. So I'm going to walk you through 2 homework problems, and I'm going to help you out with a way to kind of organize your work and make this look good. We're doing a Maclaurin polynomial, and we're centered around c equals 0. I know that in my formula I used a. A and c are basically interchangeable here. So when you see c in the homework, it's basically representing a. We're centered around c equals 0 because we're doing a Maclaurin. So let's make a table here. The first column in your table is going to be n. We're doing a n equals 4 polynomial. So my column is going to read 0, 1, 2, 3, 4. The second column is going to be the nth derivative of x. The nth derivative of x, or f of x. Well, the 0th derivative is just the original function. So the 0th derivative is e to the 4x. Now we just take each derivative from there. The first derivative is 4e to the 4x. The second derivative is going to be 16e to the 4x. The third derivative, 64e to the 4x. And the fourth derivative, 256e to the 4x. The third column of your table is going to input that c value into those derivatives. So using that derivatives that you just took, input your value of c, which is 0. That's going to be quite nice for this problem, because e to the 0 is just 1. So my column can be filled up pretty quickly. It's just 1, 4, 16, 64, 256. The last column in your table is going to take that value and put it over n factorial. Basically, each coefficient has that form, right? You put it over n factorial. Well, when n is 0, 0 factorial is 1. So we're going to put it over 1. 1 factorial is also 1. 2 factorial is 2. So 16 over 2 is 8. 3 factorial is 6. 64 over 6 reduces to 32 over 3. And 4 factorial is 24. So that also reduces to 32 over 3. So those are the coefficients of each term. I'm going to take those coefficients and I'm going to put them in front of x minus 0 to the power of n. That's going to yield us this 4th degree Maclaurin polynomial. And that's all there is to it. Okay, one more homework problem. This time we're doing an nth Taylor polynomial centered at c. So f of x is 2 over x, n equals 3, and c equals 1. So the first column in your table is going to be n 0 through 3. The next column is the nth derivative of f of x. Well, the 0 derivative is the original, so that's 2 over x. I'm going to write it as 2 times x to the negative 1. That's going to help me make my derivatives pretty easily. The first derivative, minus 2x to the negative 2. Second derivative, 4x to the negative 3. Third derivative, negative 12x to the negative 4. My third column is plugging in my desired c value, which is 1, into that derivative value. So 2 times 1 to the negative 1 is 2. Down the line, plugging in 1 again, we have minus 2, 4, and minus 12. My last column is putting that derivative value over n factorial. These are going to be my coefficients of my terms. So plugging that derivative value over n factorial. First one, 2 over 0 factorial is 2. Minus 2 over 1 factorial is minus 2. 4 over 2 factorial is 2. And finally, minus 12 over 3 factorial is minus 2. So those are my coefficients of my terms. So my Taylor polynomial looks like this. 2 minus 2 times x minus 1 plus 2 times x minus 1 squared minus 2 times x minus 1 cubed. And that is my Taylor polynomial.